All right, chemistry, this is the last new material before you take your test, and this is on stoichiometry with gases. So I thought we'd run through a few sample problems because really there's nothing new here. We're just tying the pieces together. So everything that we've learned about gas laws, we're now going to tie into everything we already know about stoichiometry. So I want to start with just an example problem. I'm going to start with this one right here. I've got some potassium chlorate, and it's going to be decomposed to create some oxygen gas and some potassium chloride. So that's going to be our starting point for this. We're going to need a balanced chemical equation. They want to know in the end, though, how much or what volume of oxygen gas will we get. So our first step is to write out our balanced chemical equation. And I can see that I'm starting here with some potassium chlorate. So again, need to have your periodic table in your green sheet. Okay, I'm going to look up my potassium. Okay, potassium is a K. It's a +1 charge. And then I look for my chlorate. That's a polyatomic ion that's on my back of my green sheet. Okay, and I find the chlorate, ClO3, and it's a -1 charge. So KClO3. And that's +1, -1, so that's a good formula. We're going to add to that. Oh, no, we're decomposing it. So in other words, we are just going to put our arrow here to make our oxygen gas. Remember, that's a diatomic molecule. And some potassium chloride, so some KCl. And we do need to go through and balance this. So again, when I look at balancing this, I see that I have 3 oxygen here, 2 oxygen there. Easiest thing to do is to make those balance out first. So I'm going to put a 2 there and a 3 there. That means that I now need to put 2 there to balance this out. If I wanted to add in my physical states, I started with this as a solid, and then I'm going to get this as a gas, and I'm going to end up with this as a solid. So those are the decomposition that we're going to go through. All right, so now time to do the actual reaction. Oh, we need to add in our given information. I always like to add in my given information here, so that 15 grams of potassium chlorate, and it's going to be decomposed, and then the gas, the oxygen gas we're going to collect is going to be at 745 mmHg and at 275 degrees Celsius. So they gave me a pressure, they gave me a temperature, and we're looking for the volume. So I'm setting it up a little bit like a gas law problem, and I'm going to kind of get myself to that point. So again, we're stoichiometry going to take this right here, convert it into this right here. So the thought process is I need to get this into moles, and then once I have the moles of the oxygen, I can then use that in my gas law step. So transfer, switch over to the new stuff, use some gas laws. Okay, so let's go through and set up this stoichiometry problem. So we've got my 15 grams of KClO3. We need to figure out our molar mass of the potassium chlorate. Okay, so my potassium is 39.10. My chlorine, chlorine is 35.45, and then oxygen, we got 3 of those at 16. So let's add all that up. Okay, so we got 39.1 plus 35.45 plus 16 times 3. So that comes out to be 122. So we're going to go 122.55 grams of KClO3 to 1 mole of KClO3. We're now going to go through and convert our moles. So 2 moles KClO3 to 3 moles of O2. Now we're going to stop here at this point because now we're going to get our mole amount. So that's what I really want, is I want to get to the moles of oxygen, so then I can use the ideal gas law. So I'm going to put an equal sign there, and we're just going to go through and figure this out. So 15 divided by my 122.55 times 3 divided by 2 comes out to be 0.184 moles of O2. So now I really know my moles of O2. So I know my N, I know my P, my V. I do need to add 273 here. So that's 548. Just going to double check that. 273 plus 275. Oops. Make sure. 273 plus 275, 548 Kelvin. Okay, so now we go into our PV equals nRT. We're looking for the liters, so I'm going to do my 745 millimeters of Hg. My V is what I'm looking for. My N is 0.184 moles. And my R, now this is where you have to go again back to your green sheet. Look for your R values. Okay, so I'm looking for an R value. It's that 62.4. And then my T is 548. We're now just going to solve for this. So I'm going to take my 548 times 62.4 times 0.184, divide that by 745. So it looks like my volume comes out to be 8.45. Now that'll be liters of O2. Okay, so that's how we kind of set that stoichiometry problem up, and we work our way through with that. On to another one. So this is another one, and actually I shared a video here that shows this reaction as well as the next reaction. So we're going to go ahead and show you both of these. So here's our first one. We're going to start with 20 liters of oxygen gas. Now if we had 20 liters of oxygen gas and it's at certain conditions, and we're going to react it with sugar, okay, C6H12O6, then we want to know how many grams of the sugar would be used. Okay, so we want to go through and first do a balanced chemical equation. So we're going to start with our sugar, C6H12O6. Now this is a combustion reaction. We're going to add some oxygen to it. We're going to make our CO2 and our H2O. Now we just need to go through and balance this. And again, when I do combustion reactions, I always balance carbons first, hydrogen second, and then save oxygen for the end. So when we look at this, I've got 6 carbons. So let's put a 6 here. I've got 12 hydrogen. We'll put a 6 there, so 12 times 2 is 6. Or excuse me, 6 times 2 is 12. Now I count up all my oxygens on this side. So 6 times 2 is 12, plus 6 is 18. 6 of them go right there, so that means that I only need to have 12 left. So let's put a 6 right there. Let's see, 6, 12, 18. So there we go. We've now got the balanced equation. Now again, I like to list out all of my information that I know. So I know that I've got, of my oxygen, 20 liters. So I know the volume. And we know that it is at a pressure of 115, 1.15 atms, and a temperature of 22 degrees Celsius. So we'll add 273 to that, and that becomes 295 Kelvin. And now what they're looking for is how many grams of the sugar are we going to use. So again, it's kind of a reverse of what we just saw. I'm going to go through and I'm going to have to figure out from here, how many moles do I have so I can do my stoichiometry to go into the other substance. So let's first do that step where we're going to just do our mole or our ideal gas law. So we'll set this up with PV equals nRT. I know my P is 1.15. My volume was 20. The N is what I'm now looking for. Now, because this is an ATM, so I'm going to go back to my green sheet and check here. My ATM one is the 0.0821 constant, so 0.0821. That's ATM liters per moles Kelvin. And then we use our Kelvin temperature of 295. And so now we're just solving for N. Okay? So N is just going to be, we'll divide, N will be equal to, so this is where I'll grab my calculator, my 115 times 20 divided by 0.0821, divide that by 295, so I come up with 0.950 if I keep three significant figures. And that's my moles of my O2. Now I just go through and set up my stoichiometry problem. So I'm going to put moles of O2 on the bottom, moles of the C6H12O6 on the top, 1, 2, 6. Then switch from my moles, C6H12O6 to grams, C6H12O6. I need to then figure out my molar mass. So carbons, 6 times 12.01, hydrogen, 12 times 1.01, and oxygen, 6 times 16. Okay, so let's go through and figure that out. So 6 times 12.01 plus 12 times 1.01 plus 6 times 16, so 180.18. So now we just go through and do our math here. So our 0.95 divided by 6 times 180.18, 28.5 grams of C6H12O6. So again, two different reactions that we got a chance to see. They both directly tied into the video that is also linked in. Let's go ahead and do one more example. So I want to take and do one more example of one that we would probably see in a lab situation, especially if we had more time. This is one where we're actually going to use a piece of magnesium. We're going to add it to some hydrochloric acid. The hydrogen gas is going to be collected, and we know what the conditions are, so we want to know what is the volume that we're going to collect. So let's go through and first create our balanced chemical equation. So we've got magnesium. We're adding it to hydrochloric acid. Now that's HCl. I think we've seen that enough now that you probably are starting to recognize that as the formula for hydrochloric acid. We know that this is going to be a single replacement reaction. And what we're going to do is have our hydrogen come out of the reaction, have our magnesium go in to the solution, and so we're going to get that situation right there where we just need to put a 2 there to balance it out. Now, we know exactly how much magnesium we're going to start with, so it's 3.25 grams of it, and we want to figure out how much hydrogen we're going to make. And this is going to be the volume that we're looking for, but we do know our pressure and our temperature of this. So the pressure was 99.5 kilopascals, and temperature was 25 degrees Celsius. So that's 298 Kelvin. And so now we can go through and, again, use this information to figure out our moles of the H2. Convert that into moles of the Mg, and then convert into our, go the other way, excuse me. Convert grams into moles here, convert this into the moles of H2, and then finally solve for our volume. So again, we're just going to set this one up. And so it's going to be our 3.25 grams of magnesium. Grams of magnesium down on the bottom, moles of magnesium on the top. Grab our periodic table, look up our magnesium, 24.31. So now we do our moles of magnesium to moles of hydrogen. It's a 1-to-1 ratio. We're going to stop there because we just need the moles. So let's go ahead and figure this out. So 3.25 divided by 24.31 equals 0.134 moles of H2. And now we can go ahead and do our ideal gas law. So our PV equals nRT. Pressure was given to us. That was 99.5 kilopascals. The volume is what we're looking for. The moles we know. The R, we're back to picking out a gas law constant. So this one actually is in kilopascals. So I'm going to choose the one that's in the kilopascals. So that's the 8.314. And now we're going to go times our temperature, which is 298. Okay, and so now we'll just go through and let's go back here and do our algebra. So 0.134 times 8.314 times 298 divided by 99.5. Volume comes out to be 3.34 liters. So we'd need a pretty big balloon in order to hold all that. But that would be how we kind of go through and do stoichiometry with the addition of the gas laws. If you do have any questions, make sure you reach out and ask. And enjoy your day after this.